All right, so we are going to revise questions based on these topics here. Okay, so there are concepts there on the more concepts. Okay, there are questions that I've put that are on dimensional analysis. Of course, the dimensional analysis that you find in chemistry, not the one in physics. Okay, so that is just simply how you are converting units, okay, from one unit to the other, but you're using what? Dimensional analysis. And then I've also put questions on concentrations. Okay, so how can we deal with questions that have uh, concentrations involved? Okay, the molarity, okay, all those things. We're going to discuss questions on those. Okay, so if you have any questions, please feel free to ask. So I'll start from the very basic concepts and then we'll be building up to the other concepts just like that. All right, so we'll start with this question here. Okay, so we're going to solve this question and make sure that you ask questions where you do not what? Understand. Okay, so let me just start. Okay, so these questions here, the three questions, they are on atoms, isotopes, and the isotopic abundance. Okay, I'm sure you've done this in class, okay, or you've heard of them, okay, if you haven't done of them. So we start with the definitions there. Okay, so they're saying define the terms atom, isotope, and mass number. Okay, so I believe everyone here knows how to define an atom, right? Okay, so an atom, we just say it's the smallest particle of an element. That's what we used to say at grade 12. Okay, the smallest uh, particle of an element, that's what an atom is. Okay, but when you come at the university level now, you'd like to enrich your answer. Okay, so you say it's the smallest particle of an element, okay, that retains the chemical properties of that element. Okay, so that's the proper definition of the atom, or you can also define it in your own way. Okay. All right. So that's the definition of what an atom is. And then we know that the atom will consist of three subparticles. Okay. There will be the protons, which are just positively charged. There will be the electrons, which are negatively charged. And then you also have the neutrons, which have a zero charge or are not charged. So these protons here, okay, their work in the atom is to give the identity to that atom. Okay, so each atom that you can think of, or each element that you can think of, has a unique proton number. Okay, so oxygen is oxygen because its proton number is 8. You will never find any other atom on the periodic table that has the proton number 8. So the number of protons, they give their identity to that atom. Okay, they give the identity to that atom. And then when you talk about the electrons, these ones here, the electrons are used for the interaction of that atom with other atoms or that element with other elements. Okay, so when you are talking about bonding, okay, covalent bonding, it might be ionic bonding. Okay, those things are going to be facilitated by these particles, which we are calling as electrons. So the electrons are responsible for the chemical behavior of the what? Of the given atom or element. And then these neutrons here are responsible for making what we call as the isotopes. Okay, so here, as I was also saying, we define the isotope. So by definition, the isotope, okay, these are just forms of the same element. Okay, there's forms of the same elements that have the same proton number, but they have different number of neutrons. So because they have different number of neutrons, they're going to have a different mass number. Okay, so also we can define what mass number is. So the mass number is just the summation of the protons that you have in that atom plus the neutrons that you have in that atom. That's the definition of the mass number. So you can define it in your own words, but just don't run away from the main idea. Okay, so the mass number is simply the total number of protons and neutrons added together, okay, in the atom's what? Nucleus. Okay, so these uh, neutrons here, I've said they are responsible for making what? Isotopes. Okay, they are responsible for making isotopes. The electrons, these are for chemical behavior. Okay, so chemical bonding, chemical behavior of that said atom or element, it's as a result of the electrons. And then the protons, these are for the identity. Okay, therefore the identity of the atom that you have or the element. Okay, so another thing that you have to know is that these electrons here, they don't move. Okay, they don't move. They're just stationary in the atom like that, in the nucleus. Even the neutrons, they do not move. Okay, but their number can differ. And then the electrons are the ones that move. Okay, because they are involved in the chemical bonding. So the electrons can be lost or they can be gained, okay, in ionic bonding, or they can be shared in what? Covalent bonding. So those are the things that you have to know, okay, on the protons, neutrons, and the electrons there. Okay, so we've defined these three terms, okay? Define these three terms. We move on to the next one. And I also wrote down the definitions down here. So you can actually read them at your own time. These ones here for these definitions. Okay, the next question they're saying chlorine consists of two isotopes, chlorine 35 and chlorine 37. If the average atomic mass is 35.45 atomic mass units, calculate the percentage abundance of each isotope. Okay, so now we know the formula for the relative atomic mass, right? Or some people, they call it as the average atomic mass. So the formula for the relative atomic mass is that it's going to be equals to, okay, the mass number of an isotope. Okay, let's say this element has two isotopes, isotope A and isotope B. So it will be the mass number, okay, of isotope A multiplied by its percentage abundance. Okay, and then plus the mass number of isotope B multiplied by its percentage what? Abundance. Okay, so this is the formula for finding the RAM or the relative atomic mass. Some people call it the average atomic mass, but it's the same thing. Okay, so now look at this question here on 2. They have said chlorine consists of two isotopes. There's chlorine 35 and chlorine 37, right? So if the average atomic mass is this one, so meaning that the RAM there they have given us, okay, to be 35.45. And they're saying now calculate the percentage abundance of this isotope. Okay, so from this notation here, when they say chlorine 35 or chlorine 37 there, if they haven't given you, okay, the mass number for those isotopes, then you are going to use those same attached numbers as the mass numbers. So it means if I'm taking the 35 one as an isotope A, and then I'm taking this one, this has 37 as isotope B, okay, it will be isotope A has the mass number 35. Isotope B has the mass number 37. Okay, so I'll say our mass number here for isotope A is simply 37. Then the mass number, okay, of isotope B is simply 37 there. Okay, so now I want to find the percentage abundances. So I want to find this percent and this percent. So I'll say for isotope A, let its percentage be X. Okay, and then for isotope B, let its percentage be what? Y. Okay, someone has their mic and mute. Let me just mute them. Okay, so only unmute yourself, guys, when you when you want to ask a question. Okay, so that you don't disturb the class. So we're saying here, the percentage abundance for isotope A is X. The percentage abundance for isotope B is Y. Okay, so we know that a percent is out of 100, right? So meaning that when I add this X plus the Y, I should get what? 100. Okay, so now I'm going just to replace these numbers that I've put here into this formula. So this is 35.45 is equals to the mass of this guy, said is 35, multiplied by the percent of A. So the percent of A percent is always over 100. So I forgot to put the 100 there. So it will be X divided by the 100 like that, because it's a percent. Okay, and then plus here I have 37 plus, okay, 37 plus, and then on the other side, what am I going to have? I'm going to have, oh, this is multiplication. So 37 multiplied by the percent for the B. So for the percent for the B, okay, it was Y. So First of all, I'll just express it as a y here, and then over 100. If you want, you can put 100 minus x. So meaning here, I'm going to have 35.45 is equals to 35x over 100, okay, plus 37y over 100. Okay, and then I can multiply here throughout by 100 so that this denominator 100 goes away. So if I multiply by 100, what I'm going to get is that on my left side there I have 35.45, okay, multiplied by 100. So that gives me 3,545 is equals to, here, if I multiply by 100, it will just be 35x plus 37y. Okay, so this is the equation that I have. Then the other equation that I have now was this guy here, where we're saying if I add x plus y, I'm going to get 100. And then if I express y, okay, in terms of x, I'm just going to get 100 minus x, right? So where there's y here, I'm now going to put the 100 minus x. Okay, but if you want, you would have put it just here. It will still work. So I'll erase this part, and then I'll have 35.45 is equals to 37x, okay, plus 37, and then here I'm going to have what now? Here I'm going to have y, not y, but 100 minus x, like this. So I've replaced this y with 100 minus x, and then now I can multiply. So this is 35.45 is equals to 35x, okay, plus this multiplied by this, it will be 3700 minus 37x. Okay, so now this one is correct. It's going to work. Okay, so here like terms together like we did before. So 35.45 minus this guy goes to the other side. So it's going to be 3700 is equals to 35x minus 37x. So here on my left-hand side, what am I going to get? So I have 35.45 minus 3700. Okay, so I get minus 155 is equals to, then here I'm going to get minus 2x. So what I have is minus 2x is equals to minus 155. So I just have to divide by minus 2, divide by minus 2. So the percentage of the isotope A, which was this x here, will just be minus 155 divided by minus 2. Okay, so I get positive 77.5. Okay, and this one will be a percent like that. All right, so any questions there, guys, on how we found the percentage? Any questions there? Okay, so don't make the mistake that I did. Okay, make sure you divide the abundance percentage by 100. Okay, and then you can find your answers like that. So we found the percentage for X, it's 77.5. Okay, meaning we can easily now find the percentage for the what? For the Y. So let's find the percentage for the Y. So for the Y, we're just going to use that equation that we made where we said Y is equals to 100 minus X. So this will be equals to 100 minus the X is 77.5. So this will just be equals to 100 minus 77.5. So that gives me 22.5%. Okay, so the Y is 22.5%. Okay, so we are going to say, therefore, the percentage abundance, okay, for chlorine 35 is simply 77.5%. Okay, and the percentage abundance for chlorine 37 is simply 22.5%. Okay, so that's the answer for part 2. So any questions there on what we've done? Okay, so if there are no questions, let's look at part 3. So part 3 is the same concept. So we're just solidifying whatever we have learned on question 2 with question 3. So question 3 now they're saying an element X, okay, has 2 isotopes. There is this X29 which has this mass, okay? And there's this X30, which has this mass. So here we've been given the masses. So we are going to use this mass and this mass. But if you haven't been given the masses, you just use the one that is attached to that same what? Atom. Okay. All right. And then they're saying the average atomic mass, which is the same as the relative atomic mass, is this. Determine the percentage abundance of each isotope. So we're doing the same thing that we did on question 2. So I'm going to say the RAM is 29.30 is equals to. And then here in the brackets, I'm going to put, okay, the mass, okay, for the first isotope, which is X29. So that is 28.976 multiplied by the percentage abundance that we don't know. Okay, so we'll say let that percentage abundance be A%. Okay, and then plus here now we're getting the mass of the second isotope, which is 29.974 multiplied by its percentage abundance. So we're just going to say its percentage abundance is B%. Okay, so we know that if I add this percent and this percent, I should get 100. So meaning A plus B should be 100. Okay, meaning that B is the same as 100 minus what? A. Just like we did for the Y, it was 100 minus X. So now here, let's replace these things. So it will be 29.30 is equals to 28.976 multiplied by, this one here is a percent. So I'll write it as A over 100. Okay, plus this one is 29.974 multiplied by, this one is a percent. So I'll write it as B over 100. Okay, so if you want, you can replace this B here with 100 minus A just from here, and then you solve. But if you want, you can replace it later. So what I'm going to have here is 29.30 is equals to this number here multiplied by A, that is 28.976 A over 100 plus, okay, 29.974 B over 100. Okay, and then here I want to eliminate this guy here in the denominator, the 100. So I'll multiply throughout by 100. So if I multiply throughout by 100, this guy here becomes 2930 is equals to, if I multiply this, it will be 28.976A. So the 100 and the 100 will cancel. Plus, if I multiply 100 multiplied by this, the 100 and the 100 will cancel. So I just remain with 29.974B. Okay, and then when we reach this point now, we can replace the B with the 100 minus what? Minus A. Okay, so let's erase what we have on top. And then we write 2930 is equals to 28.976A plus 29.974, and then the B, okay, the B there has been given as 100 minus what? A. So I write 100 minus A here. Okay, and then from there, what do? We just multiply this 29 with whatever we have in the brackets. Someone has a question? I heard someone saying, sir. Oh, all right. So on my left, I still have 2930 is equals to, here I still have this guy, 28.976A plus this number here multiplied by 100. Okay, so that one will just give me a 2997.4. Because multiplying by 100 is the same as moving this decimal place 2 times. Okay, and then minus this guy here multiplied by the A. So that would be 29.974A. Okay, so that is what we have there. So from there, we are going to say, let's put the like terms together. Okay, so 2930, this guy here goes to the left. So it will be minus 2997.4 is equals to 28.976A minus 29.974A. So you can see we've put everything on the common side, right? Okay, and then we just subtract now. So we subtract and we see what we're going to get. So on my left, I have 2930 minus 2997.4. If I subtract, I'm getting minus 67.4 is equals to, okay? And then this one here, it will be 28.976 minus 29.974. So this one is going to give me minus 0.998 A. Okay, so to find the value of A, I'm just going to divide both sides by this minus 0.998. Even this side minus 0.998. So what do I have there? We see that this guy is going to cancel. Okay, so I just remain with A is equals to, and then I divide this on my calculator. So it will be minus 67.4 divided by minus 0.998. Okay, so there I find my percent to be 67.53507.014. So I can round this off to 2 decimal places. So it will just be 67.54%. Okay, so that is my percentage for the first isotope. Okay, let's calculate the percentage for the other one. The other one will just be easy because we're just going to use subtraction. So we're using this. So the B is equals to 100 minus the A, which is this guy. So 67.54. So this will be 100 minus 67.54. So this gives me 32.46%. Okay, so the abundance for the first isotope is 67.54%. And then the abundance for the second one, okay, it's 32.46%. All right, so any questions there?
Okay, my question is like on the first equation there, where you used to say A plus B is equals to 100. What if we say, what if we use A is equals to 100 minus B? Is it okay or not?
It is okay. You can still use that one. So it's not
All right, all right.
restricted. It's not restricted to use BA. B, I was just using BA. But if you'd want, you can make A the subject. So you have A is equals to 100 minus B, right? So it means in that equation that we made, the first one, we are going to replace A so that the whole equation is in terms of B. So you can also use that one.
All right, all right. I get it.
All right. All right. So we'll move to the next set of questions. So these questions here, they are on molar mass and just moles. Okay. So molar mass and the mole concept. So let's do these ones. Okay, so the first one there is grade 12 work. Very easy to find the molar mass, right? Okay, so they're saying question number 4. Calculate the molar mass of each compound. So the first one is Al2, and then I have SO4 multiplied by 3. Okay, so how do we find the molar mass? Okay, we just go to the periodic table and get the mass numbers for these elements here, or get the molar masses for these elements. So here I have aluminium, I have sulfur, and I have oxygen. So when I go to my periodic table here, okay, for the aluminium, the mass number is this guy here, okay, which is 26.981538. So you always round off, okay, the molar mass to 2 decimal places. So meaning if I round off this one, then my molar mass for the chlorine will just be 26.98. So this is what I'll be using in my calculations. Then for the sulfur, it's this guy here. Okay, that's the molar mass. So that is 32.065. Okay, so round it off to 2 decimal places. So it's going to be 32.07. Okay, so that is for sulfur, this is for aluminium. And then for the oxygen, it's this 15.9994. So round it off to 2 decimal places, you're going to have 16.00 like this. So this is for the what? For the oxygen. So these are the ones that we're going to use for the first compound that we had there, which is this guy here. Okay, so I'll still use the same method that you guys were using at grade 12, or maybe I'll use another one. I won't use that one. So here we have two of this aluminium, right? So the aluminium, what is its molar mass? Okay, so aluminium is 26.98. And then I'll say plus. So here, most of you get it wrong here. So there's this SO4 in the brackets, and then there's this K3 outside, right? So this 3, okay, is multiplying everything inside here. Okay, so since we have one sulfur inside here, it means I'll just multiply that one sulfur by 3. And then since we have 4 oxygens here, I'll multiply that 4 by 3. Okay, so I'll say plus 3 multiplied by the molar mass of sulfur. So sulfur, we said it was 32.07. Okay, and then I'll say plus, let me change the kakara. So I'll say plus, and then now for the oxygen, I have 4 already inside, and then I'm multiplying by K3 outside. So that is like 4 multiplied by 3. So that is like 12, right? So that is 12 multiplied by the molar mass of oxygen, which is just 16. So this is what is going to give me the molar mass. So now I just punch all this onto the calculator. So I'll say 2 multiplied by 26.98 plus 3 multiplied by 32.07 plus 12 multiplied by 16. So what am I going to get there is this guy. So I'll get 342.17, and we know the units for the molar mass. This is just grams per mole. Okay, so that's how we find the molar mass. If you want, you can use what we are using at grade 12. So if, for example, I have water here, H2O, you are saying at oxygen, it's 1. I can only see 1. I multiply by its molar mass. Then the hydrogen, I can see 2 of them. I multiply by its molar mass. Okay, you get the total there, get the total here, and then you add. You can still use this. You're still going to find the same answer anyway. All right, so let's move to B. This was part A. So B, we have calcium, and then OH, and then 2 outside. Okay, so I'm going to say for that one, we're going to have calcium. We just have 1 calcium there. Okay, so what is the molar mass of calcium? So I go to my periodic table. Calcium, where are you? So calcium is here. So the molar mass is 40.078. So I'll round off to 2 decimal places. So it will be 40.08. Okay, that's for calcium. All right, so that will be, calcium is just 1. So that will just be 40.08 plus, here I have oxygen inside these 2 brackets, and then I got 2 outside. So the K2 is multiplying the oxygen and then multiplying the hydrogen. So it means I have 2 multiplied by the oxygen plus 2 multiplied by the molar mass of the hydrogen. So the hydrogen, its molar mass is just 1.01 if you round it off to 2 decimal places. And then you punch this whole thing now onto the calculator. So it will be 40.08 plus 2 multiplied by 16 plus 2 multiplied by 1.01. So I get my molar mass there to be 74.1 grams per mole. Okay, so that's how we can do that one. Let's do part C. So if you have any questions, just unmute yourself and then you ask. So part C, we have C6, H12, and then O6. So now it's 6 multiplied by the molar mass of carbon, which is 12.01. You can check it from the periodic table, plus 12 multiplied by 1.01 plus 6 multiplied by 16. So this will be equals to, okay? So now I just punch everything onto my calculator. So 6 multiplied by 12.01 plus 12 multiplied by 1.01 plus 6 multiplied by 16. So I'm getting 180.18, and this is grams per mole. Okay, so that's how we find the molar mass there. The next thing, we go to question 5. Okay, so question 5, it's a bit interesting than question 4. So question 5, they're saying how many moles are contained in whatever they have given us there. Okay, so there's some concept that we need to use. A and B, it's the same concept because we've been given mass there. And then C, it's a different concept because we've been given the number of molecules. Okay, so let's start with A. So we know the formula for finding moles. Okay, it's just moles indicated by N is equals to the mass that you've been given over the molar mass. Okay, so the mass that I've been given there is 25 grams divided by the molar mass of magnesium. So what is the molar mass, okay, of the molar mass of magnesium? Okay, so you go to your periodic table. So magnesium is there. So that is 24.3050. So I round it off to 2 decimal places. I'm going to have 24.31. So that's what I'm going to use. So I'm going to say 24.31. Okay, so when I divide this, what do I get as my moles? 25 divided by 24.13. So this one gives me 1.028 um, 1.028 and then 383381. Okay, so since this one here had 2 significant figures, you can also try to express your answer with the same significant figures. Okay, but if you want, you can just round it off to 3 decimal places, or even 2. So let's do 2. So 2 decimal places, this will be 1.03, and these are moles. Okay, so that's part A. Part B, it's the same thing. To be moles is equals to 180, okay, grams over the molar mass of glucose. Okay, so now you need to know the formula for the glucose there. Okay, so the formula for the glucose is what we found there. Okay, and remember, the molar mass that I found for the glucose was 180.18 grams per mole. So that's what I'm going to divide with here. Okay, so that will be 180.18 grams per mole. So if I divide this, what will be my moles? So I have 180 divided by 180.18. Okay, so it gives me 0.999000999. Okay, so if you round it off to 2 decimal places, you're just going to get 1.00, and these will be moles. Okay, so that's how we can find the moles. And then let's do the interesting one now. So that one, they're saying how many moles are contained in 2.5 times 10 to the power 23 molecules of carbon dioxide. Okay, so there you just have to make use of what requires the Avogadro's constant. That's all. Okay, so the Avogadro's constant states that 1 mole, okay, of anything that you can think of, okay, 1 mole of anything has 1 mole of anything has 6.02, okay, 6.02 2 times 10 to the power 23 particles. Okay, so these particles will be dependent on what you're talking about. Okay, so the particles, they can be ions, they can be electrons, okay, they can be atoms, or they can be molecules. Okay, to just be depending on whatever you are talking about. So 1 mole of anything contains 6.022 times 10 to the power 23 particles. So in this case, we're talking about what? Molecules. Okay, we're talking about molecules. So if 1 mole contains 6.022 multiplied by 10 to the power 23 molecules, okay, What about if I have 2.5 times 10 to the power 23 molecules? How many moles am I going to have? Okay, so where there's moles here, you can just write X. And then you simply cross multiply like that. So it will be X multiplied by this whole thing, and then this multiplied by 1. So I'll just get 6.022 multiplied by 10 to the power 23. X is equals to 2.5 multiplied by 10 to the power 23. Okay, and then from here, we want to find this X. Okay, so I'm going to divide both sides by 6.022 multiplied by 10 to the power 23. Even this side, 6.022 multiplied by 10 to the power 23. Okay, so it means on my left-hand side, I'm just going to remain with X. So it will be X is equals to, and then I just have to divide this on the calculator. Okay, so I can show you a good way or a trick, okay, in dividing such numbers. So these ones that have 10 to the power something, you separate them from the numbers. So it will be 2.5 over 6.022. Then I'll say multiplied by 10 to the power 23 divided by 10 to the power 23. Okay, and then I can just punch this now on my calculator. So 2.5 divided by 6.022. So that one gives me 0.415. Okay, I've just rounded it off to 3 decimal places. Then multiplied by this one here. This is 10, this is 10. The base is the same. So it is 10, and then I can subtract the powers since I'm subtracting them. I'm dividing them, I mean. Okay, so you see that those things are just going to cancel. We're just going to remain with 1. Okay, so this will be 0.415 multiplied by 10 to the power 0, which is 1. So I'm going to get the same answer. So these are moles. Okay, so 2.5 times 10 to the power 23 molecules of carbon dioxide, okay, are equivalent to 0.415 moles. All right, so any questions there, guys? Okay, so if there are no questions, we look at question 6, this one here. I hope you guys are understanding, okay? If you have questions, please don't feel shy, just ask, okay? So that you get to also learn how to do it. So number 6, they're saying calculate the number of atoms, okay, in 0.5 moles of calcium nitrate, okay? Calculate the number of atoms in 0.5 moles of calcium nitrate. Okay, so what can we do here in order to find this number of moles? Okay, what can we do here in order to find this number of we're calculating the number of atoms, right? So what can we do here in order to find the number of atoms in 0.5 moles of calcium nitrate? Okay, so calcium nitrate has the following formula. So it is Ca and then NO3 and then 2. So this is calcium nitrate. Okay, so how am I coming up with this formula? This is calcium, so I write Ca. And then nitrate is a radical. So that radical is simply NO3. So now the valence for calcium is 2. And then the valence for the nitrate, okay, the valence for the nitrate is 1. So when combining them, the calcium gets the valence for the nitrate, and then the nitrate gets the valence for the calcium. So this one goes to this one goes to this. So no wonder I have C, and then NO3, and then 2. As simple as that. So this is the formula, okay, for calcium nitrate. So now we want to find how many atoms are contained, okay, in 0.5 moles of this calcium nitrate. Okay, so this one is a trick question. Looks simple, but it's a trick question. But I'm going to show you how to do it. Okay, so this one here, the way I've written it here, just this formula here. Okay, this formula here is one more on its own. Okay, so in this formula, okay, so one more of this formula here contains how many atoms from what we can see here? Okay, it has the calcium 1, it has the nitrogen multiplied by 2, so it has 2 nitrogen. Okay, and then it has oxygen 3 inside the brackets multiplied by these 2, so it has 2 multiplied by 3 oxygen, so it has 6. So it has 1 calcium, 2 nitrogen. Okay, so I was explaining that this one, okay, this one compound here, or one molecule of the calcium nitrate, okay, it has how many atoms in it? So there is 1 calcium, 2 nitrogen, and then 6 oxygen, like that. So the total atoms that are present here, okay, in one molecule of this is just 9 atoms. Okay, so in one molecule of this, I can write the ratio now. In one molecule of this compound, okay, I have what? 9 atoms. Okay, so now I have to find how many atoms are in 0.5 moles of this. So I know that 1 mole, okay, of anything, okay, contains 6.022 multiplied by 10 to the power 23 molecules. Okay, so now what about if I have 0.5 moles? Okay, how many molecules am I going to have there? So I have to cross multiply. So it will be x multiplied by 1. That will just be x is equals to 0.5 multiplied by whatever I have here. So that will be 0.5 multiplied by 6.022. So that gives me 30, not 30, but 3. Okay, it gives me 3.011 multiplied by 10 to the power 23 molecules. Okay, so meaning that 0.5 moles of calcium nitrate is the same as 3.011 times 10 to the power 23 molecules. And then now, from this ratio that we had developed earlier, we're going to find the number of atoms. So from this ratio, we said one molecule of this whole thing here, okay, has 9 atoms. What about if I have these molecules? How many atoms am I going to have? So it will be, let me erase this line here. So I'm using that ratio now. It will be, I have now 3.011 times 10 to the power 23 molecules. Okay, how many atoms am I going to have? So I'm going to cross multiply there. So it will just be x multiplied by 1. I get x is equals to, then this multiplied by 9 atoms. So it will be 9 multiplied by 3.011, okay, multiplied by 10 to the power 23. And this will be our number of what? Atoms. So x will just be, so I multiply 3.011 multiplied by 9. Okay, so I get 27.099 multiplied by 10 to the power 23 atoms. Okay, so those are the number of atoms that are contained in 0.5 moles of calcium nitrate. Okay, so any questions there? Okay, so if there are no questions, then we are done with these questions here. So what did I do first? I converted the moles to the number of molecules, okay? And then the number of molecules to the number of atoms using this ratio here. Okay, so that's how we moved on question 6 there. All right, so we move to the next set of questions. This is on percentage composition as well as the empirical formula. Okay, so there, they are just determining the percentage composition, okay, and then also finding the empirical formula. So the first one, they're saying determine the percentage composition of nitrogen and oxygen in NO2. Okay, so how do you find the percentage composition? Okay, so you find the percentage composition by, okay, saying the molar mass of a certain atom that you want to find the percentage composition for, divided by the total molar mass from where it's coming from, and then you multiply by 100. So here I want to find the percentage composition of nitrogen and oxygen in here, right? So it will be percent of nitrogen will simply be equals to, okay, the molar mass of nitrogen divided by the molar mass of NO2, then multiplied by 100. So in the same way, the percent composition of oxygen would just be the molar mass of oxygen in NO2 divided by the molar mass of NO2, then multiplied by 100. Okay, so I know the molar mass of nitrogen, so you can confirm from the periodic table. To 2 decimal places, it's 14.01 grams per mole. And then for the oxygen, it's 16.00 grams per mole. Okay, so let's first of all find the molar mass of NO2. So NO2, it will be 1 nitrogen, which is 14.01 plus 2 multiplied by the oxygen, which is 16 like this. So this will be 14.01 plus 32. So when I add this, what do I get? So 32 plus 14.01. So that will give me a 46.01 grams per mole. So that is the molar mass of the NO2, okay, or the nitrogen oxide. So now here, percentage of nitrogen will just be equals to the molar mass of nitrogen there. It's just 14.01 divided by the molar mass of NO2, that is 46.01, then multiplied by 100. Okay, so that's what we do. And when I do that, I'm getting, I'm getting the answer as 30.449902195%. So I can round it off to 2 decimal places. So it will be 30.45%. Okay, so that's the percentage composition of the nitrogen. And then now we find the percentage composition of the oxygen. Okay, so for the oxygen, I'm going to say percent of the oxygen is equals to. So now notice that in NO2 here, we have 2 oxygens. Okay, so it means the molar mass of oxygen is going to be multiplied by 2 because we have 2 of them there. So it will be 2 multiplied by 16 divided by the molar mass of this NO2, which is 46.01 multiplied by 100. Okay, so what do I get as my percentage composition for the oxygen? I get 69.550097805. So this is what my calculator is saying. I round it off to 2 decimal places, maybe. Okay, I'm going to get 69.55%. Okay, so the percentage composition of the nitrogen is 30.45%. Then the percentage composition of the oxygen is 69.55. Okay, so make sure that when you add those two, you get 100 or a number that is very close to 100. So if I add this plus this, I'm getting 100%. Okay, so that just confirms that whatever you're doing is actually what? Correct. All right, so any questions there, guys? Okay, if there are no questions, we move to question 8. So question 8 is on empirical formula. I sent a video where I was solving the assignment for chemistry. Okay, so I solved all those questions there, and they were all on percentage composition and empirical formula. Okay, so I expect you guys, some of you watched the video. If you didn't, I'll reshare it in the group anyway. Okay, all right, so oh, someone is asking, are these A levels? Yes, they are. Okay, so here they're saying a compound contains 40% carbon, 6.7% hydrogen, and 53.3% oxygen. Find its empirical formula. Okay, so the usual method is just to follow whatever I'm going to write here. So I'll say element here. I have carbon, I have hydrogen, and then I have oxygen. And then here I write mass percent. So this one is 40. This one is 6.7. This one here is 53.3. Okay, so the next one is now to find the moles. So how do we find the moles? We divide each of these mass percent with their molar masses. So this will be 40 divided by 12.01. And then hydrogen, it is 6.7 divided by 1.01. This one here is 53.3 divided by 16.00. So what do I get there as my number of moles? Okay, so for the first one, I get 3.3306. Okay, then if I divide 6.7 divided by 1.01, I'm getting 6.6337. Okay, so I'm just rounding off to 4 decimal places. And then the other one is 53.3 divided by 16. I'm getting 3.33125. Okay, so once you find the moles now, the next thing is to find the ratios. So these ratios, how are you going to find them? You're going to pick the smallest number of moles that you can see here, and then divide by that number of moles throughout. Okay, divide by that number of moles throughout. So which one is the smallest number there that I can see? The smallest number that I can see is this guy here, the first one. Okay, I can see that the first one is the one which has the smallest number. So I'll divide throughout here by the 3.3306. So it will be 3.3306 divided by itself. And then this one will be 6.6337 over 3.3306. This one will be 3.3312 divided by 3.3306. So the first one, if I divide, this is just going to be 1 because they're the same. Then the second one, let's do it. So I have 6.6331 divided by 3.3306. So I find 1.9916. And then the other one is 3.3312 divided by 3.3306. So I'm finding 1.0002. Okay, so those are my ratios there. So can I round off these ratios? Yes, because they meet they satisfy the conditions for rounding off. Okay, so there are some times when you find these ratios and you cannot just round them off anyhow. Okay, the video, for example, the video that I sent yesterday. Okay, we had ratios that you cannot just round off anyhow. Otherwise, you're going to get the wrong answer. So in that video, I was saying you can only round off, okay, if a number is between two specific values. Okay, so I'm going to say x.2 and then I'm going to say x.8. So if a number is between x.2 and x.8, so this x here can be any number, okay, can be any number. So if I'm talking about this one here, then the x will just be 1, okay? So if you draw like something like a number line, you put x.2 somewhere there, then here you put x.8. So you can put a boundary here and the boundary here. So you can only round off, okay, if the point something that you have there is less than 2. So for example, you can see this one here is 0.0. 0.0 is less than 0.2. So it will lie in this region here. So we can round off, okay? Or you can round off, okay, if your point something is greater than 0.8. So we can see this is 0.9. Okay, 0.9 is greater than 0.8. Okay, so this number here is going to be somewhere there. So we can round off. Okay, so here you can just round off normally. But there are some times when you get numbers such like 1.5, okay, 7, maybe 6. We see that the 0.5 there is greater than these two, but it's less than the 0.8. So it will be somewhere in between here. So if you have a number somewhere in between zero point 0.2 and 0.8, you can't round it off, okay, when you're finding these empirical formulas. Instead, what do? You look for a number such that when you multiply throughout, okay, it's going to give you a whole number or a number that you can round off. Okay, that's the rule when you're rounding off while finding the what? The empirical formulas. All right, but here we're just going to round off because they meet the rules there. Okay, so the first one there is just going to be remaining 1. This one round off to 2. This one round off to 1. So my empirical formula will be C, H2, and then O. So that will be my empirical formula there. All right, so any questions there? Okay, so we move to the next one. Here again, we're finding the empirical formula, molecular formula. Okay, so I'll be a bit fast here because we know what is happening. So they're saying a compound contains 52.2% carbon, 13.0% hydrogen, and 34.8% oxygen. So the first thing that you do here is try to add this, and this to see if they're going to give you 100. Okay, to see if they're going to give you 100. So I have 52.2 plus 13 plus 34.8. So if I add them, they give me 100. Okay, so determine the empirical formula. Okay, it's the same issue. So we say the elements, we have carbon, hydrogen, and oxygen. And then mass percent 52.2, 13, 34.8. And then we say moles. Okay, so I divide each of these by their molar masses. So I won't show them, I'll just be dividing on the calculator. So 52.2 divided by 12.01. Okay, I get 4.3464. And then 13 divided by 1.01. There I get 1.2, not 1.2, but 12. Okay, so 12.8713. Then here, it's 34.8 divided by 16. So that would be 2.175. Okay, and then of these moles that are found, which one is the lowest? Okay, so I'll say ratios here. So the lowest we can see is this 2 point something. So I'll divide everything here by this 2 point something. So the first one is 4.3464 divided by 2.175. So that one gives me 1.9983. Then this guy, 12.8713 divided by 2.175. That one gives me 5.9178. Then this one divided by itself, it's going to give me 1. And you can all see that this one is greater than 0.8, this one is greater than 0.8. So I can round off. So this will be 2, this will be 6, this will be 1. So my empirical formula there will be C2, H6, and then O1. But the 1, we don't show it, so just write like that. So that is my empirical formula there. So C2H6O. Okay, the other question was saying, determine the molecular formula. Okay, so the molecular formula, we just have to find the factor. So the factor is equals to the molar mass, which was given as 46, divided by the empirical formula mass. So the empirical formula mass, you get it from the empirical formula. So that is 2 multiplied by 12.01 plus 6 multiplied by 1.01 plus 16. So that will be 2 multiplied by 12.01 plus 6 multiplied by 1.01 plus 16. So my molar mass there, I find it is 46.08. So if I divide this, 46 divided by 46.08, I'm going to get 0.998263. So I can round off this. it will just be 1. Okay, so it means my factor is 1. So my molecular formula will just be equals to my empirical formula multiplied by the factor, which is 1. So in this case, my empirical formula and molecular formula are actually what? The same. Okay, so that's how we find them there. So I don't expect you guys to fail any questions on empirical and molecular formula, okay? Because we've done a lot of them. All right, I'll go to the next one, which involves combustion analysis. So this one is the one that usually gives problems to people, okay, when they involve combustion analysis. So combustion analysis is simply the burning, okay, of an unknown organic compound, okay? And then from that burning, you're going to produce carbon dioxide and water. So the good thing is that, okay, even if, okay, even if that organic compound is unknown, okay, all the carbon that it has goes on to form carbon dioxide. And then all the oxygen that it has goes on to form water. Okay, so if you've been given the amount of carbon dioxide and been given the amount of water, you can indirectly find, okay, the amount of carbon and the amount of hydrogen that was in the original sample that we are what? Combusting. So combusting simply means reacting with oxygen. So here they're saying a 10-gram sample of a hydrocarbon. Okay, so here they've even made it clear. So hydrocarbon simply means it contains carbon and hydrogen what? Only. So this guy here, we can call it X, which is the hydrocarbon, was reacted with oxygen. That's what it means to combust. And then it produced carbon dioxide plus the water. Okay, so the mass of this is 10 grams. The mass of this is 3.0 grams. The mass of this is 13 grams. Okay, so if I can find the amount of carbon that was here, I'm indirectly finding the amount of carbon that was there. Okay, and for the hydrogen, the same. So I'm going to say mass of carbon is equals to, okay, so here I'm going to use the ratio for the molar masses of how much carbon is in the carbon dioxide and then multiply by the mass of the carbon dioxide that we are given in the question. So I know that carbon has a molar mass of 12.01 divided by the molar mass of the carbon dioxide, which is just 44.01. Okay, and then this I'll multiply by the mass of the carbon dioxide that was I was given in the question, which is just 33, like that. So if I multiply this, it's going to be 12.01 divided by 44.01 multiplied by 33. Okay, so when I do that, I get 9.005. Okay, 9.005. I'll end there. So this is grams. So this is how much, okay, this is how much of the carbon dioxide is contained in this. I mean, how much of the carbon is contained in this 33 grams of the carbon dioxide. Okay, and then the mass of hydrogen will be equals to, in this water, I have 2 multiplied by the molar mass of hydrogen. So meaning the molar mass of hydrogen in water, it will be 2 multiplied by its molar mass, right? The molar mass of hydrogen is 1.01. Multiplied by 2, I get 2.02 divided by, okay, the molar mass of water is 18.02 multiplied by the mass of the water that I was given there, which is simply 13.5. So this will be equals to, so in brackets, you say 2.02 divided by 18.02 multiplied by 13.5. Okay, so what I'm going to get there will be simply 1.5 1 3. Okay, so I'll end there. Okay, so I found the mass of the carbon. Okay, I've also found the mass of the hydrogen that was contained in the hydrocarbon that they burnt, or the hydrocarbon that they actually combusted. Okay, so I found that. So now the next thing here is simply to um it's simply to find the empirical formula. Okay, so these numbers here I was rounding them off, but this is not the final answer, so I feel we should not round off there. So I'm going to write the whole number that the calculator gave me here, so that we are accurate. So this one was, I'll do it again. So it was 12.01 divided by 44.01, right? Then I multiplied by 33. So I'll get the exact calculator value. So this was 9.005453306, so that we are accurate. Then this one was 2.02 divided by 18.02 multiplied by 13.5. So this one is going to give me 1.513318535 grams. Okay, so that's the mass of carbon and that's the mass of hydrogen there. Okay, so the next thing now is to, because we're calculating the empirical formula, right? The next thing is to calculate the moles. Okay, after the moles, we calculate the ratios, and then after the ratios, we calculate um, what? Our empirical formula. Okay, so since we have the masses now, okay, if you want, you can find the percent. Uh, Someone has their mic and mute. I can hear myself. Okay, let me just mute them. Okay, so right, so we can go directly and use these masses to find the empirical formula, or if you want, okay, or if you want, okay, or if you
If you fail to answer, Google before tomorrow because you only have today to Google. Tomorrow.
Someone is saying something. Is that Natasha? You want to ask a question, or it was just a mistake? Okay. All right, so let me just mute everyone. Okay, so I was saying we can find the empirical formula using these masses, okay, or if you want, you can actually first find the percent compositions, okay, so that they are in percentages like these ones here, because percentages are easier to handle, okay. So I'm going to say, let me find the percentages here. So I'm going to say percent for the carbon is just 9.005453306 divided by the total mass of the sample, which is 10 multiplied by 100. Okay, so what am I going to get there? So 9.00545 3306 divided by 10 multiplied by 100. Okay, so the percent that I'm getting there is 90.05. Okay, I'm getting 90.05%. And then the percent for this was with the percent for the carbon. So the percent for the hydrogen will be the mass, okay, of the hydrogen divided by the total mass of the sample, which is 10, multiplied by 100. So this is going to give me, okay, so I have 1.51 18535 divided by 10, and then multiplied by 100. Okay, so there I'm finding what percent now? Okay, so there I'm finding okay, so I'm finding 10.15%. Okay, so those are the percentages that I'm finding. So from here now, I can find my empirical formula. So I'm going to use this percent and this percent here. Okay, so let's do that now. So I'm going to say element here. So the element have carbon and hydrogen, and then the mass percent is 90.05, and then I found 10.15. From there, I find the moles. Okay, so I divide each of these by their molar mass. So the first one is 90.05 divided by, okay, 90.05 divided by 12.01. So that one is going to give me 7.4979. Then this one is 10.15 divided by 10.15 divided by 1.01. So that one gives me 1.004. Okay. Sorry, here it doesn't give me 1, but it gives me 10.0495. Okay, so those are the moles. And then which one of these is the smallest? So we see the smallest is this one. So I'll find the ratios there by dividing by the smallest. So it will be 7 divided by itself, I get 1. And then this 10, okay, 0.0495 divided by 7.4979. Okay, so there I'm getting 1.340. I'll just end it there. So now look at the ratios that we've actually found here. Okay, look at the ratios that we've actually found here. So the ratios here are 1 and 1.3. So this one here, we can't just round off to become 1. No. Why? Because this one, the 0.3 there, is between the x.2 and the x.8. Okay, so the 0.3 is between somewhere here. So we can't round it off. So instead, we are going to look for a number such that when we multiply throughout, okay, it's going to give me a whole number or a number that I can round off. Okay, so if you have 0.3, okay, or 0.6 or 0.9, you always first try to multiply by 3 throughout. Okay, so the pattern is like this. If you have 0.2 something, okay, if you have 0.2 something, always multiply by 4 first. If you have 0.3 something or 0.6 something or 0.9, 0.9 you can't because you can round off. Okay, if you have 0.3 or 0.6, you have to multiply by 3. If you have 0.5 something, okay, you have to multiply by 2. So that's the pattern there. Okay, and then you starting to guess and trying out all the numbers. So this is 0.3 here. So I'm just going to multiply throughout by 3. So this will just be 3. Okay, and then if I multiply this by 3, what do I get? So 3 multiplied by 1.340. So I get 4.02 like this. Okay, so yeah, so this now is 0.0. The 0.0 will be somewhere there, and I can actually round it off. So this will just be 3, this will just be 4. So the empirical formula there will just be C3 and then H4 like that. Okay, so it will be C3H4 there. All right, so any questions there on the empirical formula and the molecular formula, as well as combustion analysis, you can ask if you have a question. Any questions there? Okay, so let's move to the next section. Here we are just solving some questions where we are balancing the equations. Okay, because I was just picking some questions from different concepts under stoichiometry and more concept. So the other thing that you have to know in chemistry is how to balance equations. Okay, so how to balance equations, there are actually about 3 standard methods that we use. Okay, so the first one is when you're balancing something in acidic media. The other one is when you're balancing something in basic media. The other one is when you're balancing an equation using oxidation numbers. But for today, I'm not going to talk about those ones. Okay, those are the 3 standard ones that you find in chemistry. And then there's also what we call balancing by intuition. So just using your intuition, you're able to balance a chemical equation. So that's what we are most using at grade 12. So this is also what is required on this question here. Okay, because I can't see any ions, I can't see any electrons. So we're going to balance it by intuition. So the first one is Al, which is aluminium, plus O2, giving me Ol2 and then O3. So we balance this by intuition. So first of all, we balance any other atom apart from oxygen and hydrogen if you have it in that equation. So let's try to balance Al. So Al, on my left, I only have one. On my right, I have two of it. So it means I'm going to put a 2 in front of Al there. So meaning that I have 2 aluminium now on my left and 2 aluminium on my right. And then you take a look at the oxygen. The oxygen here, I have 2 oxygen. Here I have 3 oxygen. So how can I balance them? Okay. So you notice that if you have 2 and then on the other one you have 3, you can just multiply these by the opposite numbers. So I'll multiply this by 2 and I'll multiply this by 3. You see that I'm going to get 6 here. I'm also going to get 6. So that's what I would do. So in front of this O2, I'm going to put a 3 so that I have 6 oxygen. And then in front of this O3, I'm going to put a 2 so that I have what? 6 oxygen again. So when I put a 2 in front of this compound here, you can see that the number of aluminium have what? Increased. Okay. I no longer have 2. I now have 4 aluminium. So it means I'll go back to the other one, which is this one, and I'll just change it so that I have 4. Okay. So this 2 here, we're just going to come and erase it like this. So this is what we call as balancing by intuition. So it's like you're doing a trial and error. So this one now is fully balanced. Okay. So if you have 4 Al plus 3 O2, producing 2 Al2 and then oxygen 3. This here is balanced. Okay, this one here is balanced. All right, so any questions on that one? Okay, so if there are no questions, let's do part B. So we're still using intuition. Okay, so it's like we're doing trial and error. So here on B, we have C3H8 plus O2. And then here we have CO2 plus H2O. Okay, so we're going to first of all to balance any other thing apart from oxygen and hydrogen. So meaning that we are going to balance carbon. So you can see I have 3 carbon here, but here I have 1. So I'm just going to put a 3 in front of the carbon. So the carbon have balanced. Okay. Next, I'm going to try to balance the hydrogen. Okay. So on my left here, I have 8 hydrogens there. Then here I have 2. So how can I make these 2 hydrogens here to be 8? Just like here. I'm going to add the 4 in front there. So that will make 4 hydrogens to the left, 4 hydrogens to the right. So carbon and hydrogen have been balanced. And then I'm just remaining with the oxygen now. So now look at the oxygen. Here, the oxygen is being multiplied by 3, and then it already has a 2. So here I have 6 oxygen. Thus, there it's 4 multiplied by oxygen. So I have 4 oxygen. So it means on my right, I have a total number of 10 oxygen atoms. And then on my left, I can only see 2. So how can I make that 2 to be 10? I'm just going to add a 5 here. Okay, so now you can see that the equation has been balanced. Okay, we have equal numbers of carbon, hydrogen, and oxygen on both the left and the right side. Okay, so the last one is K, which is potassium, and then magnesium, and then O4, producing K2, M, N, and then O4 plus M, N, O2 plus O2 like that. Okay, let me write that one nicely. So plus O2. Okay, so again, we start balancing any other thing apart from the apart from the oxygen. So you can see that on my left here, I have 1K. But here I have 2. So I'll put what here? Okay, so if I put a 2 here, it means okay, anyway. So I'll put a 2 here. So it means now on my left I have 2K, even here I have 2K. What about the MN? So MN is being multiplied by 2, so I have 2MN on my left. What about on the right? On the right I have this MN and this MN. If I add them, I also get 2MN. Okay, what about the oxygen? The oxygen on my left, I already have 4 here, being multiplied by these 2. So that makes like 8 oxygens on my left. And then on my right, here, I have 4 oxygens, right? Here I have 2 oxygens, there I have 2 oxygens. So when I add all of these, I also get 8 oxygens. Okay, so I just had a 2 in front of the K there. Then the whole equation there is going to be balanced. All right, so any questions there on balancing the equations? Okay, so if there are no questions, let's move to the next subtopic. So this one now is stoichiometry and limiting reagents. So here you have to pay attention of whatever is going to be happening, okay? Because there's more of the thinking here than whatever we've been doing. Okay, so I was starting with the simple things and then I'm increasing just like that. So here you have to know how to use the mole ratios. Okay, you have to know how to determine the limiting reactant. And then it means in your all your calculations, you're going to use the mole ratio of the limiting reactant, okay, to the product that you want to find. Maybe the mass or maybe the moles. So number 12, okay, they're saying hydrogen gas reacts with oxygen to form water. And they've given us the equation there. Okay. Check if the equation is balanced. Yes, it is balanced. And then they're saying if you react 4.0 grams of hydrogen gas with 20.0 grams of oxygen, determine the limiting reactant. Okay, so the limiting reactant is the reactant that finishes first in the chemical reaction. So because it finishes first, it determines the amount of product that is going to be produced. Okay, so some of you, what you do here, you just see the one that has the smaller mass and then you say that it's the limiting reactant. Okay, so that is wrong. You have actually to prove it using calculations. So how do you do that? You first calculate the moles, okay, of those independent reactants, and then you relate them using their molar ratios. You see which one will be uh, which one will not be enough, okay, and which one will not be will be in excess. Okay, so let's first of all find the moles of the hydrogen gas. So hydrogen gas is H2 there. So I'll say moles of hydrogen gas will just be equals to, okay, so moles is equals to mass over molar mass. So it will be the mass that have been given 4.0 divided by the molar mass of hydrogen gas. So that is 2.02. Okay, so this will just be 4 divided by 2.02. So that will just be 1.98019802. Okay, so these will be the moles of the hydrogen gas. And then I also calculate the moles of the oxygen gas there. So the moles of the oxygen gas, what is the mass of the oxygen? It is 20 divided by what is the molar mass of oxygen gas? So 1O has 16. What about 2 of them? They will have 32. So that will be 20 divided by 32. I get 0.625 moles. So these are the moles of oxygen. These are the moles of hydrogen. So now I want to determine which of these is the limiting reactant. Okay, so from the balanced chemical equation there, you can see that 2, okay, moles of hydrogen gas require 1 mole of oxygen gas. Okay, I can just get the coefficient there. There I have 2, here I have nothing, so meaning I have 1. So now, what if I have 0.625 moles of the oxygen? Because this is hydrogen, this is oxygen. How many moles of the hydrogen am I going to require? So you do a cross multiplication here. So it will be x is equals to 2 multiplied by 0.625. So I get 1.25. Okay, so these moles of oxygen here require 1.25 moles of what? Hydrogen. Okay, so now when I look at what I have in my equation, okay, when I look at what I have in my equation, you see that the moles of hydrogen that I have, they are 1.98 something, which is above the 1.25, I mean. It's greater than the 1.25. So it means that the hydrogen is in excess, okay? And oxygen is the limiting reactant, okay? Because the moles of oxygen that I have here only require 1.25. But in my equation, I have these moles of hydrogen. So it means these guys are in excess. So the limiting reactant will just be what? The oxygen. So the limiting reactant there, we are going to say that the limiting reactant is the oxygen. Okay, so oxygen is the limiting reactant. Okay, so it means that now in all our calculations, okay, we're going to be using the ratio, okay, of the oxygen to the product because it's the limiting reactant. So let me just write the initial moles of hydrogen somewhere here in case we need to use it. So 1.98019802 moles. Okay, so we found the limiting reactant, which is oxygen or O2, and then they're saying find the mass of the water produced. So to find the mass of the water produced, we're going to use a mole ratio between the limiting reactants and the product water. So you see that from O2 to water, what is the mole ratio there? The mole ratio is 1 to 2. Okay, because there is 1 in front here, here there's 2. So now, if I have 0.625 moles of oxygen, how many moles of water are going to be produced? So cross multiply, I get x is equals to 2 multiplied by this guy. Okay, 2 multiplied by that guy. So if I multiply 2 multiplied by that, okay, I just get 1.25. This will be moles of what? Water. Okay, but the question was asking for the mass. So since I have the moles of water, I know the molar mass of water is just 18.02 grams per mole. So since I have the molar mass and I found the moles there, I can easily find the mass. Okay, so I'll say mass of the oxygen. Hey, mass of the water, not oxygen, sorry. Of the water produced is just going to be equals to. So remember, moles is equals to mass over molar mass, right? So if I make mass the subject, it will be mass multiplied by 1. So mass is equals to N multiplied by molar mass. So the moles, we found it's 1.25 multiplied by the molar mass, it's 18.02. So this will just be equals to 1.25 multiplied by 18.02. Okay, so the mass I find for the water is 22.525 grams. Okay, so 22.525 grams. So that is the mass of the water. Okay, so any questions there, guys? Okay, so let's move to the next one. So the next one, they're saying determine the excess reagent remaining. Okay, so we know that the moles of oxygen were just 0.625 moles, right? Okay, so to find the excess reagent remaining, they mean the mass of the hydrogen that is remaining. because part of it is going to react with the oxygen. Okay, so first of all, I have to find how much of the hydrogen gas reacted with the oxygen. Okay, and then if I find that how much hydrogen gas reacted with the oxygen, I can simply subtract from the initial moles that I had. So if I get a mole ratio there from hydrogen to oxygen is 2:1, and then if my oxygen is 0.625, what would be my X? Okay, you're supposed to write 1. Okay, the ratio is 2:1. So cross multiply, its X is equals to 2 multiplied by this, which is 1.25 moles. So it means 0.625 moles of oxygen reacted with this moles of what? Hydrogen. So it means initially I had these moles of hydrogen, and then these ones reacted. So meaning excess moles, okay, excess moles of hydrogen will just be equals to the initial 1.98. We can round it off to 2 decimal places, it's fine, minus this one here, which reacted 1.25. So if I subtract that, what do I get? So 1.98, I mean, minus 1.25. So I find the excess moles is 0.73 moles. So now we have to change this excess moles to mass. So the molar mass of hydrogen is hydrogen gas is 2.02 grams per mole. So meaning mass of the excess hydrogen gas will just be the moles multiplied by the molar mass. So this will just be 0.73 multiplied by 2.02. Okay, so the excess mass that remains is 1.4746 grams. So from the 4 grams that we had, okay, some of the masses has reacted with the oxygen. The one which is in excess, or the one that remains, is 1.4746. Okay, so meaning if they even ask you the question like what mass reacted, you can simply say 4.0 minus whatever we found here. That is the mass that reacted. Okay, so any questions there? Okay, so if there are no questions, I'll solve the last question. Okay, because we started like at 12, this is almost 14. So you guys need to rest. So I'll stop at question 13, and then we'll have another class at 17. I'll see. If I want, I can start it at 16, if I'm free at 16, so that we cover the rest of the concepts. Right, so let's look at question 15, which is still on these limiting reactant things and such. Okay, so here they're saying when 15.0 grams of calcium carbonate is heated, okay, it decomposes to form calcium oxide and carbon dioxide. Calculate the moles of calculate the moles of calcium oxide produced, the mass of calcium, the mass of this is what carbon dioxide released. Okay, so they have said calcium carbonate. So calcium carbonate is CaCO3. So they heat this thing up, okay? Then it produces calcium oxide plus calcium dioxide. Carbon dioxide. Okay, so want to find the moles of calcium oxide produced. So make sure that your equation is balanced, and this equation is already balanced. Okay, so let's find the moles of the calcium carbonate. So that would just be equals to the mass that have been given there divided by the molar mass of this. So the molar mass of this guy is the molar mass of calcium, okay, which is 40.08 plus the carbon 12.01 plus 3 multiplied by the oxygen. So what do I get there? So you get these molar masses from the periodic table. So it is 40.08 plus 12.01 plus 3 multiplied by 16. So it gives me 100.09. Okay, so the moles here will just be 15 divided by 100.09. So the moles of calcium carbonate are 0.149865121 moles. So here there's no need to find the limiting reactant because we're just burning this calcium carbonate or heating it. So meaning the heat is in excess there. Okay, so there's no need to find the limiting reactant. So now A was saying find the moles of calcium oxide produced. So I see that the mole ratio there is 1:1 of this guy and this one. It's just 1:1. So meaning that the moles of calcium carbonate are actually equal to the moles of calcium oxide. So we're just going to write this number here because their mole ratio is 1:1. Okay, so those are the moles. And then B, they were saying, okay, here, they're saying mass of carbon dioxide released. So if we want to find the mass of carbon dioxide, we first have to find the moles, okay, and then convert those moles to mass. So again, the mole ratio of this guy and this guy is just 1:1. So their moles are the same, still this number here. So to find the mass of carbon dioxide, I'll just multiply its moles multiplied by the molar mass. So its moles is the same because the mole ratio is the same. So it's just 0.149865121 multiplied by the molar mass here for the carbon dioxide there is the molar mass there is 44.01. Okay, so I just multiply this now. Okay, so I find the mass to be 6.06 grams. Okay, so this was the mass of the carbon dioxide that was what? Released. Okay, I think for the first class we can end here. Okay, we'll resume at 17 or 16. I'll communicate in the group. But there's still some questions that we need to solve. Or if you want, if you have questions that you would like us to solve, just send them in the group. Okay, send them in the group, and then I'll put them on the board here. I'll show you how to solve them. Okay, so we are going to do questions on percentage yield. We haven't done these. Solutions and concentrations, and then composition of solutions and dimensional analysis. Okay, so we are left with about 4 concepts that we have to cover. Okay, so if you have any other questions, please forward them so that we solve them in the next class. All right, so any other question before I close this class? Okay, so if there are no questions, I can actually show you guys our website. So on our website, we have lessons to all the topics that you are going to learn under NS. Okay, so you can use it to learn at your own time, at your own pace. So if you go on our website, okay, if you go on our website, you're going to see something like this. Okay, let it just load here. Okay, so these are the courses there. So you can see math, chemistry, biology, physics. So you can subscribe for any of these courses that you want. Okay, so for example, if you go into chemistry, you go in the folder for general chemistry. Okay, you're going to see that you're going to find all the topics that you're going to do in chemistry. Okay, so there are videos there are notes that you can use. So if you're having difficulties with any of these courses, okay, that you are doing under NS, you're having difficulties in any of these topics, we already have summarized videos there and notes for you. So if you go in this first folder, you're going to find lessons on everything, okay, under chemistry there. So you can see all these topics there. The ones that you've learned, the ones that you haven't learned yet. You can see the more stoichiometry, solutions, whatever you want is there. Okay, so you can actually subscribe to our website and you'll be able to access this content. And also we have solutions to tutorial sheet as well as the past papers. So you can see here, you're going to have past papers, they are going to have tutorial sheets. So you can use them to learn at your own pace, at your own time. Okay, and we also have a mobile app for this website. So on the mobile app, you can actually download the videos and watch them even offline. Okay, so just go to Play Store, you search Discrete Learning Institute. The app is going to come. You can install it, create an account, and then log in. You're going to find all these here, or if you want, you can still use the website. All right, so thank you so much for attending, guys. I'll see you in the next class.